Okay, so we are starting thermodynamics, which is different than thermochemistry. And thermochemistry, that was in Chem 161, where we talked about heat and processes that release or absorb heat. And now we're really going to get into not only the heat, but the energy associated with each reaction, what makes a reaction happen versus reactions not happening. So we're going to start with a term that is not necessarily what you think of when you think of the word spontaneous. So a lot of the times in the English language, spontaneous means it happens by itself. In chemistry, that is not necessarily what we mean by a spontaneous process. So I'll get to exactly what we mean here in a little bit, but we are going to start with the first law of thermodynamics, which is really just conservation of energy. And we talk about this all the time, right? Cannot be created or destroyed, only transferred. So for like the 100th time now, right? Energy can only be created or cannot be created or destroyed. Cannot be created or destroyed, only transferred. So essentially what that means is we can change it from one type of energy to another, but it's never going to go away. Okay, so we can use that as energy. It can be potential energy or kinetic energy. And the way that we transfer energy is by heat and or work. Okay, so this is kind of like the physics of it. This is where thermodynamics comes in. So if you ever take P-Chem or physical chemistry, one of those semesters is thermodynamics. Okay, so this was chapter 5, so 161. Essentially, we talked about the fact that the internal energy of a system, the energy in general, is related to the kinetic and the potential. Those are our two main types of energy, right? So Ke is kinetic. Pe is potential. Okay. And then I introduced the term enthalpy. Enthalpy and heat for us are really synonymous. That we'd usually use the term delta H to show change in enthalpy. Is the amount of internal energy. So this is the same E. This is the total amount of energy plus this really stands for the work. Okay, so if we said it can only be transferred by heat or work, the heat part is the energy part, and the work part would be if you change the volume at a certain pressure. So this is really like expanding or contracting gases. That's why P times delta V. Now, we're not going to use this equation to actually calculate work. We're going to focus really on the heat part, but work does play in here. So if you have a gas expanding or contracting, then that's like work being done. So I'm going to go back to this word, the spontaneous, right? So we say something is spontaneous in chemistry does not mean that it just happens by itself. Okay. So there are some shortcomings with our first law. So we're talking about the fact that energy has to be transferred, can't be created or destroyed, but that doesn't actually tell us to what extent a reaction happens, right? So we talk about equilibrium and things don't go completely forward or completely backwards. So we need to take that into account. So a shortcoming of the first law is that it doesn't tell us to what extent a reaction happens. And again, what I mean by that is the whole equilibrium aspect. A reversible reaction is going to go forward or backward. It kind of depends. Now, this whole idea of thermodynamics is really, it's very different from kinetics. Kinetics is what we talked about in our very first chapter of this semester. And that's like how fast it's going to go, the pathway that it takes, what is the mechanism. We are focusing on the thermodynamics. The thermodynamics just factors in or just looks at where we start, so like our reactants, versus where we end or our products. Okay, so thermodynamics is essentially the initial to the final. We don't actually care about how we get there. Okay, you could add up all of the delta H's for a reaction, and like the overall process is just based on where you started and where you ended. The process is not what matters. Okay, so kinetics is the how. Okay, if you add a catalyst, blah, 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 blah. The thermodynamics is just the heat. So this is where we are focusing. Okay, so this is our chapter 19. This was back in chapter 13. So we don't actually care about this part right now. We're just focusing on the beginning and the ending. Okay, so I have an important key phrase here. Reactions are said to be thermodynamically favorable. Okay, so spontaneous in chemistry is equated with thermodynamically favorable, meaning based on the heat and the work and whatnot, it is a favorable reaction, means it's going to happen. It's going to go in the forward direction. Well, if we're talking about the forward direction, that's what's going to occur, either forward or reverse, whichever is favored. So big K, right, means it would be favored in the forward reaction. Little k would mean it's favored in the reverse reaction. Okay, so that's what we mean by spontaneous, that it is favored, not that it happens by itself. Okay, so this is my note here. Spontaneous in the chemical sense does not mean that it will happen on its own or without activation energy. Activation energy is still a thing. You can be favored, but need activation energy. Okay, so we are focused on the term it is favored. That's what spontaneous means in chemistry. Okay. For example, if you light something on fire, it might need activation energy to get going, but after that, it is going to give off heat. It's going to continue by itself. So it does need activation energy, but it is favored to react. Okay, so I'm going to look at two different processes. So if a forward reaction is favored, then the reverse reaction is not going to be favored. So which of these two reactions, so this is the same reaction, it's just flipped. Which one is spontaneous? Is it spontaneous to break water into hydrogen and oxygen? Does that happen? Is that more favored, aka the electrolysis of water, breaking it up? Or is it favored for hydrogen and oxygen to come together to make water? This is essentially the burning of hydrogen fuel. So whenever you burn hydrogen, in oxygen, you end up with water. Which of these is more favored? Happens kind of on its own, again, ignoring that it needs activation energy. Well, that is going to be, of course, the burning of hydrogen fuel. Reason being, once you spark hydrogen, it is going to go. It is going to go crazy. You're going to have all of these reactions happening. Okay. This is the Hindenburg blew up, right? You get a spark and boom, everything reacts. In order to actually break up hydrogen and oxygen, in order to do this reverse process, which is the first one here, you actually have to put in energy, you have to put in work in order to actually break all of those molecules up. So that is not favored. The one that is favored would be burning hydrogen fuel. Okay, so this one was not favored because it requires work. Okay, the whole time. You have to continually put in energy in order to break these up. Okay, this one is favored because it's very exothermic, gives off a lot of energy, and happens once it's given the activation energy. Okay, so it might need a little spark to go, but then it just kind of happens by itself. All right, we're going to look at these two processes now. So which of these is spontaneous? The forward reaction, in which iron reacts with oxygen to make iron oxide, or iron oxide breaking back into iron and oxygen. Well, iron oxide is rust or oxidizing, versus if we want to get rid of rust, we need to reduce that. And we actually have to set up essentially an electrolysis reaction. So if you think about it, you'd be like, oh, well, this happens all by itself. This is spontaneous, right? And that is true. This reaction here is considered a thermodynamically favored or a spontaneous process, right? This happens easily. Once it's given whatever it needs to react, it happens by itself. The only way to actually get rid of it is to reduce, have to, again, do work. We have to do something, which in this case is electrolysis. And we're going to talk about electrolysis and what that is, how to reduce and oxidize in the next chapter. Okay. So those are kind of some examples of determining whether the forward or the reverse reaction is spontaneous based on reactions we're familiar with. Now, what about reactions we're not familiar with? What causes something to be spontaneous or thermodynamically favored? Okay, so this is what we're really looking at. My question is, what is thermodynamic favorability dependent on? How do you know something is going to be favored or not? What do we have to look at? Okay, so there are really two main parts to this. Okay, the first is temperature. Okay, energy change, exothermic, endothermic. We're going to look at that. The second is we'll talk about in a little bit, but I'm really going to focus on temperature first because this one we are most familiar with. All right, so temperature, which is oftentimes the most important factor. I'm going to look at water going from solid to liquid. So this would be like ice to liquid water, right? So this is the process of melting. Okay. This process is spontaneous. Is it spontaneous for it to melt above or below 0 degrees Celsius? Well, you'd be like, well, spontaneously, ice melts above 0 degrees Celsius, right? So if you're at a certain temperature, this process is spontaneous. If you are below that temperature, that process is actually not spontaneous. The reverse reaction would be spontaneous. Okay? So we would say reverse is spontaneous below 0 degrees Celsius. And this is true for all substances. They have a specific temperature at which they, well, not all substances, melting and boiling and all of that. Let's just focus on that. For all processes of melting, boiling, phase changes, essentially, there's a specific temperature at which it is spontaneous in the forward direction or spontaneous in the reverse direction. Okay, so there are other factors that play in though. Okay, so I'm going to talk about diamond and graphite here for a second. Okay, so if you look at the 3D structures of diamond, this is the 3D structure of the carbon molecules in diamond, and this is the 3D structure of the carbon molecules in graphite. Diamond, we know, is much more stable, right? It's really, really hard to break down a diamond, whereas graphite, you can just kind of like use, it sloughs off in sheets, essentially. And that's because it really only has a 2D structure, whereas diamond really has a 3D network of carbon bonds, okay? So turning diamond into graphite, is that a thermodynamically favorable process? Okay, and it actually is. Turning diamond into graphite technically would be a thermodynamically favorable process, but then you're looking at like, well, if I have a diamond, even if I put in a bunch of energy, it's not just going to turn into graphite, right? The opposite is true if we're looking at the other way. We do have to put in a lot of energy in order to get graphite to turn into diamond. So why is it that this is technically thermodynamically favored? Okay, so we have to look at something other than just endothermic, exothermic. Okay, so technically, like I said, this is a thermodynamically favorable process to turn diamond into graphite because it's a lot harder to go the other way. And it really just has to do with its structure and stability. So we also have to look at that. Has to do with structure and stability also. Okay, so just kind of keep that in mind. It's not thermodynamically favorability and spontaneity are not just based on endothermic and exothermic. Okay, so we're going to talk about processes that are reversible. So this is irreversible because remember I said we have to bring in this whole equilibrium idea as well. So I'm going to start with reversible processes, right? So like phase changes and reversible chemical reactions, like what we've talked about previously. Okay. So reversible is essentially a change where the system and the surroundings can be returned to their former states by exactly reversing the change. Okay, so if I'm going from solid to liquid, I can exactly reverse that to get back to solid by taking the energy out, essentially. Okay, so a reversible process is a change where, and I'm not just talking chemically, this can be chemical, physical, both the system and surroundings can be returned to the former state by exactly, it's important, the reverse change. Okay, so like I just said, phase changes are like this. If you take energy out versus put energy in, you have to use the exact amount to get it to go backwards. Equilibrium reactions are also this, of course. Equilibrium reactions, okay, where they reach a steady state are always reversible. When you're talking about equilibrium reactions, and like I added stuff in, it reached equilibrium. I can stress it, it'll get back to equilibrium. If I add stuff or take it out, I can get it to go back. All right. So these are our reversible processes, whereas we also have processes that we would consider irreversible. Okay. And you're probably thinking of some chemical reactions, right? Like I burned something and now I have a bunch of ash. I can't just send it backward. And you're absolutely right. So irreversible processes are a change where the system and surroundings cannot be reversed without altering the system or surroundings in some way permanently. So irreversible is a change where system and surroundings cannot be reversed without altering the system or surroundings permanently. Okay, so I'm going to use kind of a more simple example, not a chemical example. If I had, so this is a piston, this is a partition, I've got gas over here, and I have a vacuum over here. If I remove that partition, okay, I take it out, we know that gas is going to expand to fill the container. So the gas filled the container, and I don't have a vacuum anymore. Now I can't just put the partition back and separate it, right? The gas is already spread out. The only way to do it is if I actually change the system. I have to move this piston to get it all back down to separate it out, okay? So we can like reverse the process, but you kind of have to put work in order to do that. So here we did work was done to change the container in this case, change the container. Okay, so it's going to expand in there. I can't just put it back in and it'll reverse. It doesn't work like that. Okay, this is irreversible because it required work done by the surroundings to change it. So to go backward, I actually had to do work. Okay. Same thing. This is a picture of if I've got a gas on one side, a vacuum on the other. I open it up. Of course, it is going to fill. It is going to spread out. That is the spontaneous process in the forward direction. To go backward, that would be non-spontaneous. Gases are not just going to spontaneously all go to one side. That's not how gases work. They like to fill the container. So the reverse reaction is non-spontaneous because it would require work. Would require work to separate. Okay, so if it requires work to actually get it to go back, it's technically an irreversible change.